Um, Good evening, everyone. Hello. Okay, so I believe we can start regardless of the number that we have currently. Okay, so I will share. Okay. So please, can I get a thumbs up or anything to indicate if you can see my screen? Okay. Okay, so today we are supposed to look at section 2 of DCIT 102. Our last meeting for 102, we looked at section 1, and it's very important that we move on to section 2. And then we look at how we can move on from there. Because now looking at the time that we are left with, we would have to double up. We would have to find a way to finish up with everything on time. So what I'm going to do, or what we are going to do, is that now after the class, we would quickly try and then finish up with the class, and then have a question and answer session. So we would look at some questions, that is MCQs, that is based on that is consistent with the mode of examination for this semester, and then we try to answer them together. And I believe that doing that would help us not only learn for knowing sake, but actually prepare for the upcoming examination. All right, so let us go straight to the slides, and let's see what we are. So the session outline is focused on the introduction to computer hardware, the main functions of the computer system, and then the functional components of the computer system, the CPU and its components, the input-output units, the storage elements, and then the system interconnections. And the number of pages are a bit huge. We have 182 pages or 182 slides in this particular presentation. So we might not be able to finish everything today. However, we would make all efforts to get as far as we can, and then we look at how best we can continue from there in our next section. Okay, so let's continue. So introduction to computer hardware. So computer hardware, as we all know, refers to the physical components of the computer. So when we talk about hardware, we are talking about the physical component that makes up a computer, the components that we can touch, that we can feel, the solid components of a computer. That is what we refer to as the hardware. So when you compare a computer to a human being, we can say that the hardware is like the body, okay? The hands, the legs, the head, the parts which you can touch, which are solid. Those are the hardware. So with a computer system, we're talking about things like the keyboard, the mouse, the monitor, and other internal components which you can touch or you can feel are all parts of the computer hardware. So microcomputer hardware can be classified into several functional units, and each functional unit is composed of several hardware devices that perform specific functions. So we are just saying that every hardware um, unit, okay, can be classified into several hardware devices that perform specific functions. And these are the different devices that comes together to form that particular functional unit, okay, of the computer system. So we will look at some of these with time and then talk about them properly. So there are four main functions of the computer system, and these four main functions of the computer system are data. Of course, we are not saying that these are the only functions of a computer system. There might be others or many more, but we are talking about the main functions of a computer system or the main purpose that a computer system serves. One is data processing. So basically, computers exist to process data, and that is the prime purpose of the existence of computers. So you feed it with data, and then the computer should have the ability to process the data and give you an output. Without this, we can conclude that a computing system might not have any use or relevance if the computer cannot process data. Then the purpose of that particular computing system is questionable. So, two, data storage. Computers also function as storage mediums. You should be able to store data. You should be able to store text. It should be able to store images. It should be able to store videos. It should be able to store audios and all other medium through which data can be represented. But we are not necessarily saying that every computing system should be able to store all forms of data. Okay, it can be numbers, it can be audios, it's whatsoever. So far as it can store any form of data, we can classify that as it functioning as a storage unit. And then three is data movement, which is input or output. That is, you should be able to move data into and outside a computing system. So we should have the ability to feed the computer with data, okay, and instructions, and the computer should be able to return an output. We just mentioned data processing here. The computer cannot process data unless you fed it with data. That is, you've sent in an input. And to do that, we need what input-output mediums or input-output devices. So computers should have these facilities available that enables it to receive data and to also output data. So assuming you buy a computing system, any computing system at all, and then you realize that the keyboard is not working, or the mouse is not working, or the touch screen is not working, automatically the computer does not serve its purpose for which it was made, because you would not be able to feed the computer with data. And I'm sure if you cannot feed your mobile phone or your laptop or any other computing system like your calculators and any other with data, then it becomes absolutely useless because it has no processing power. If you cannot feed it with data, it has no processing power if it cannot accept input. And once it cannot accept input, that means that there is no way the computer can also return any meaningful output also. And three, the computer should also function as control, okay? And this is one thing that we are going to really explain in this session. So let us go to the next session. Let us go to the next page. So others include the central units, that is the functional units. We have the central processing unit, which is a CPU, okay? So these are the basic units. When we say units, it's like how do you call it, or how do I put it? Let's say these are like the main elements, okay, that comes together to form the computer system, or these are the main as in I want to get a practical scenario to proper illustrate it. For instance, when you go to companies, you have departments, right? Each department might be kind of standalone or might be autonomous in their own way, but at the end of the day, they have to coordinate in order to assure the smooth running of the company, right? So let's say you have a company that produces vehicles. You have a department that works on the electricals. So there you might find electrical engineers. You have a department that operates or assembles the engines. Okay, you might find the mechanical engineers. You have a department that manufactures the tires, and let's say the paints that is used to spray the vehicles and all those parts. So these are different departments and they might be different units on their own, but they work hand in hand. Okay, after the units that produce or the department that produces the ties has made the ties, they do not need it for their own use. They have to pass it on to another unit for them to make use of the ties that they've created. The unit that, let's say, creates the engines have to pass it to another unit to merge it into the body, okay? And then the electrical engineers have to come in to, as in, wire everything up. So all these units have to coordinate in a way in order to create a functional system. So we are basically saying that for a computer to run as a functional system, we have to have functional units, okay, that coordinates different processes in order to make this happen. And we stated earlier that when we talk about the functional, the main functions of the computer, we talked about data processing, data storage, data movements, and control. But we are saying that for this to happen, there are some units here that have to work together to make this happen. And these units are the central processing unit, or the CPU for short, the storage units, the input output unit, and the system interconnection. So again, the central processing unit, the storage unit, the input output unit, and the system interconnection. Now, I want us to ask ourselves this question here, that what is the interconnection between the functional units and the functions of the computer? Let us draw some parallels here. You realize that we said the first functional or the first function of a computer system is data processing. Okay. So for data processing to happen, we need the central processing unit. Okay. The central processing unit is a functional unit in charge of data processing. And this is a question that can be asked in examination. That what is a functional unit that is in charge of data processing? You know, it is your central processing unit or your CPU. So when you talk about storage, data storage, okay, we need what? The storage unit, okay? And we are going to talk more about the storage unit shortly. We need our registers, we need our RAM, we need our ROM, we need everything coming together to play that particular role or function there. So when we are talking about data movement or input or output, we are talking about what are input or output units. And if we are talking about our control units here, then we are talking about what system interconnection. And this is something that you should always know at forefront. The functions of the computer and the functional units which plays those functions or which are in charge of coordinating those functions. Okay, so let us continue. So if we take a computer and we are to project into a computing system, there are some main units that you are going to find, as we said previously. And that is our central processing unit, our memory, okay, or our storage, which here is designated or denoted as a main memory. Then we have our system interconnection, and then we have our inputs and outputs. And all this coordinates hand in hand to make the computer what it is, or to make the computer a complete system. That is why when we are talking about the computer, we call it the computer system. A system is basically different units that coordinates okay, to perform a particular function. So when you take the human body, for instance, the human body is made up of different systems. We have the digestive system. The digestive system is in charge of breaking down food into food nutrients, okay, and then flushing out the waste. Okay, I think we have another system that is in charge of that. And what is that? That is the excretory system, right? The excretory system is in charge of flushing out the waste out of the system. And then we also have the nervous system that is in charge of transporting signals and as in giving you the ability to think those kind of things. And then we have the circulatory system and all those kind of things. So you can see that the body itself operates in a similar manner as well. It breaks, you can break it down into functional units, okay? And funny enough, each functional unit can also be broken down into another other set of functional units made up of devices that teams up to form that functional unit. So when we are talking about storage as a functional unit, we are not just talking about one device working as a storage medium. We'll get to find out that we have a lot of devices that teams up to form the storage unit. When we are talking about the central processing unit, so a central processing unit is not just a single device, but it is a group of interconnected devices that are working together to process data or to give a computer its processing power. And when we are talking about a system interconnection, also we are also talking about a group of devices that are working together, and then input and output. Also, we are talking about same. So let us move forward. All right, so now we are going to look at the structure of the computer system. Under section 1, we briefly highlighted this, but under section 2, we are going to go into it much, much deeper. So when you take a complete computing system, okay, you should have something like this. That is an input and output unit. I'm coming. So you should have an input unit, okay, that feeds data into the system. So the job of the input unit is just to feed data, okay, into the system. And then it's just like the human eyes, the skin, the tongue, and those stuff. Yeah, so they feed data into the system. Okay. And then you have the CPU. And we said that the CPU is the main processing power of the computer. And then we have the memory, which functions as a storage unit of the computer, because you are saying that data has to be stored in one way or the other. When you feed a chunk of data into the system, the computer does not process everything at once. It has to store some at a safe place and start processing some, okay? So after it's done processing one unit of data, it goes and fetch another unit of data and processes that also. And it does that in batches until all data has been successfully processed. So when data is fed into the system, the memory is responsible for storing the data, okay, to be used, but that is used by the CPU, or that the CPU uses to execute. And there are a lot of systems or interconnected systems that work together to ensure this is coordinated smoothly. Okay, and then we have the output medium. That is, after data has been processed, the computer returns output, okay, or the result of what it had processed. But I just want to explain this, that when we talk about storage, we are not only talking about storage in terms of input, that is before processing, okay? Even after the CPU has processed data, there are some data which are still stored or which are not out, which are not as in sent out immediately. They are still stored within the system, okay? So we'll talk about all that later. So let me get this from the of the two. So let's go to the next page of our presentation. So we have our central processing unit, and you can see. So you can see your central processing unit here. This is how our central processing unit looks like. It isn't something so big, just a small device with it. In fact, even your RAM is bigger than the CPU, okay, on a normal day. I mean, in a standard computer. But it's a very, very powerful system. Without it, a computer system will totally be useless. It will be nothing else than an input and output medium, but will have no processing power. That means that the same data that you would feed into a system, that will be the same data the system will put out, and it will not be able to output it or return an output for that. So let us look at the CPU. So the CPU is the central processing unit, and it is known as the processor or microprocessor. And please, let's take note of this. For MCQs, this is a question that can also be asked, okay? Probably they could ask you, what is another name for the CPU, okay? And you should know that that is the same as the processor or the micro processor. Or they could ask you that which device is or which computer component is known as a microprocessor. A, CPU, B, motherboard, C, whatsoever, then they add a D. You should know that that is the same as the CPU. So please, for the purpose of MCQs, which is what we are going to do in our examinations, it is very, very essential and relevant that we take note of the details, the detailing, because for MCQs, even the tiniest detail can be a question on its own. So the next is that the CPU, okay, is regarded as the brain of the computer. That is where all processing happens, okay? Just like every human being, all the processing happens within your head, which is your brain. That is the same way in a computer. The brain of the computer is a CPU. So just as a human being functions, that is a similar way that the CPU also functions. The human brain, I mean, gives you the ability to think, the ability to make decisions, the ability to process instructions, and that is the same as the CPU. The CPU gives the computer the ability to think, the ability to process instructions, and the ability to execute data. So whatever is supposed to be done, the CPU is what ensures that it is done and coordinates all those activities. So without that, a computer is basically useless. It just becomes a device that accepts input and then returns output. So the next point here is that it performs the basic operations of the computer, such as arithmetic, logical, and input and output. Okay, so it performs the basic operations of the computer, such as arithmetic and logical operations. We'll talk about that very, very, very shortly also. So the CPU performs all types of data processing operations. So we are using the term all types, okay? So every data that is processed within a computer, it doesn't matter how that data is represented, the CPU is what processes that data, okay? So if you go and feed a bunch of instructions to any computing devices or any computing device, I mean, it is the CPU that would ensure that that data is processed. And whichever output that you see, it's coming directly from the CPU. So it also controls the operation of all parts of the computer. So let us look at the components of the CPU, and this is where we need to take note of a lot of stuff here. So we have the arithmetic and logic units, and then we have the control units, we have the registers, and then we have the cache or the cache, okay? And the registers and the cache falls under our memory, okay? And we are going to talk about that. So let us look at the arithmetic and logic unit or the arithmetic logic unit. The reason why for me I prefer calling it arithmetic and logic unit is that arithmetic and logic are two different things altogether, okay? Let's not regard them as one thing. So we have the arithmetic unit and then we have the logical unit. What do we mean? We are trying to say that the CPU, okay, is basically divided into parts, okay? And when it comes to the main part that is in charge of the processing, we are talking about this, which is the ALU. So the ALU is divided into two parts. The first part is our arithmetic unit. The arithmetic unit is in charge of processing anything which is or which has to do with addition, subtraction, multiplication, and division. Okay. So anything that has to do with direct computations with addition, subtraction, multiplication, and division is performed within the ALU. Okay. So when you enter any data, such as let's say 2 plus 5, the ALU is the part of the computer that performs this particular operation. So let's say 2 plus 5 times 2. The arithmetic unit, I mean, is a part that performs this. But when you come to the logical unit, as the name suggests, performs operations with regard to logic. Okay, so when you give the computer logical operations or logical operators, okay, and when you're talking about logical operators, we are talking about comparison operators. Comparison operators like less than, greater than, less than equal to, greater than equal to, our or, our exclusive or, our and, our NAND, are not. All those things are performed within the logic units. Okay, that is the part that directly performs all those logical operations. Let us talk or let us look at the ALU into depth. So let us look at the arithmetic and logic unit. So an arithmetic logic unit, ALU, is a digital circuit component of the computer. This is the fundamental building block of the CPU. It performs arithmetical and logical operations such as addition, subtraction, multiplication, and division, just like we stated earlier. So we are saying that, look, if you take your calculator, if you enter anything with regards to direct computations, addition, subtraction, multiplication, division, you should know that it is the arithmetic unit that performs that operation. The unit also performs comparison or logical operation, such as shifting, comparing numbers, letters, or special characters. So anything that requires a computer to think, okay, that is not straightforward, direct. That do not deal with direct computations, but requires the computer to think. It is directed to the logical or the logic unit to handle. So now let us look at our registers. So the register is a collection of high-speed storage locations. Please, let's take note of the keyword. It's a collection of high speed. Let me underline that. The reason why I'm very keen on we taking notes, the details, is that these are the things that, so it is a collection of high-speed storage locations. So if they should ask which of these is a high-speed storage unit, okay, and the hard disk is mentioned, let's say the ROM, you should know immediately you see registers in there. You should know that is the answer that you are going for. Okay, so it is a collection of high-speed storage locations. Registers are temporal storage areas which are responsible for holding data that is to be processed by the CPU. Okay, so apart from them being high speed, they are also temporal storage areas. They do not store data permanently. Okay, they are not storage units that stores data on a long term basis. Okay? As in keeping data for 1 month. No. Registers are short-term memory. Okay, they are volatile. After it's done performing its operations, it just writes off. Okay, so registers are temporal storage areas which are responsible for holding the data that is to be processed by the computer. So please, you have a diagram below, and we are going to use a diagram to explain some of these concepts further. So they store instructions and data in a processor and provide fast access because of their proximity to the ALU. Okay, so we are basically saying that, look, the CPU is in charge of processing data. Okay, now if the CPU has to process data, it cannot be relying on the RAM at every point in time, or it cannot be relying on other slow data storage units for this. Else that will slow up the entire function of the computer. So basically, we have to create an intermediate storage that serves as an intermediary between the main memory and then the CPU, okay, or the ALU and the ALU, I mean. And then what this intermediate unit does, or this register does, is that it basically receives the instructions or the data that is to be performed. And after it has received it, it then keeps it, okay, so that the ALU can have direct access to it. Because it's relatively faster, it will be able to supply data to the CPU faster and then coordinate all those activities within a very short period of time without causing a computer to run relatively slower. And that is how you can be able to feed in a chunk of data to the computer, and within a flash, the computer is able to process it and return an output. It is because there are systems that have been created to ensure that this happens, and one of them is the registers. Okay, so they also store instructions and data in processor and provide fast access because of their proximity to the ALU, which is the arithmetic logic unit. Different types of registers can exist to handle different operations within the CPU. They can be classified as general purpose. This is one. So we are saying that the types of registers, we have general purpose or specific purpose, which can also be called dedicated registers. And the difference between the general purpose registers and the specific purpose registers is in their name. The general purpose registers, they store generic data, okay, or they've been created to store every kind of data, whereas the special purpose register stores only specific, they've been designated a specific kind of data that it can store. Outside that, it cannot store any other data which it has not been designated, apart from what it has been designated to store. Let us use a practical instance or a practical illustration. You see, when you go to some institutions, some institutions, you find this dustbins. Probably you would find 3 of them stationed at one place. And those 3 dustbins, they will label one, let's say, plastics only. Please, let's take note of the keyword here. Plastic only. Okay, they've added only. So in terms of registers, that becomes a special purpose or dedicated register. Why? Because it has been dedicated to plastics only. And aside plastics, it cannot store any other thing, okay? Or it is not meant for any other thing again. If you attempt to store any other thing within that particular dustbin, it defies the purpose for which that dustbin was created. And another dustbin, they might name it as, let's say, food only, okay? So that one, let's say if you eat that is where it's supposed to go. And then let's say the third one, that one, there is no inscription on it. Okay, let's say that is general purpose. If you have anything else apart from plastics that does not fit into the plastic container, or that does not fit into the second container, you store it in the third container. Okay, and the third container becomes your general purpose register. Why? Because it can store generic data. It can store any kind of data. It does not store specific, or it was not designated to store specific data only. Okay, so that is the main difference between the general purpose registers and the specific or the special purpose or the dedicated registers. One is designated to store specific, and the other can be kind of data that is available to Word. So let us look at the special purpose registers. So this category of registers is used for performing specific operations. Okay, let us look at them. They include the program counter. And what does it do? It holds the address of the next instruction to be executed. Let us come down and let me explain something here. Okay, so we can see the CPU here and we have the memory. Okay, let us look at this very carefully. If you come or if you look at the memory, the memory has been divided into several parts, and each part contains a specific set of data. Okay, so each part contains a specific set of data, and this data has been assigned an address. Okay, there is an address that is assigned to every location in the memory. Okay, so this address that the memory is holding could be instructions or they could be data. Let us take note of this. There's a difference between instructions or data. Instructions are basically commands that are to be executed. It indicates a chain or a sequence of commands that are supposed to be executed and the manner in which they should be executed. For example, an instruction can be something like 2x plus y. Now, what is the meaning of this instruction? This instruction is basically telling the CPU that take the number 2, okay? When you take the number 2, the user is going to give you the value of a variable called x. And when it gives you the value of the variable called x, multiply it by the 2, and then add the corresponding result to y. Okay, this is an instruction, and we just indicated that, right? And it follows a particular sequence. Multiply the x by 2 and then add the corresponding result to y. This is an instruction. And now, under this instruction, you need some data in order to execute this instruction. And what is the data you need to execute the instruction? That is the value of x and y. So we can say that x is 5 and then y is 3. And what happens here when you feed this data into the system? The system basically takes this data for x and then feeds it into the expression, and then takes the value of y and also feeds into the expression. So basically, it will multiply 2 by 5 and it will give us 10, and then add the results to y, which is 3, and then would return an output of 13. Okay, so this is a simple instruction that the computer can process. And then we are saying that what the computer will need, or the parameters the computer will need in order to process that particular instruction, is what is known as what? The data. So let us know the difference between the two. So the memory can hold both, that is instructions and data. And after it has held this particular data, it now passes them to the CPU in a particular style or in a particular fashion. And we are going to look at how this is done. Okay, how this is done. So basically here, we are saying that the general purpose registers, okay, that was what we were initially explaining, could hold, no, we are rather talking about the program counter, sorry. So the program counter, as we were explaining, holds the location of the next instruction to be executed. Okay, so let's say if currently the computer is executing instruction at location 0, please can we all see location 0 here? So let's say location 0, let me erase everything so that we can illustrate this. So let's say location 0 is the current location. This is a current location of the program that is being executed. So let me call this current, okay? So current program that is being executed, then automatically what will be the next program to be executed? That will be the program at location, the instruction at location 1. Okay, so location 1 will be the next. Let me call that next. So the program counter will contain the address of location 1, which is the next program to be executed, not the current program that is being executed. Okay, let's take note of that. The program counter only holds the address of the next. So assuming that currently the location of the address that is being executed is location 0, then the program counter will contain the address of location 1 because location 1 will be the next. If it's now processing location 1, the computer is now processing location 1, it will now hold the location 2 because that will be the next program to be executed. So let's kindly take note of that. Okay, so that's just the program counter and how it works. Let's look at the instruction register or IR. So the instruction register holds the current instruction being executed. Please, let's take note of the keywords for the purpose of MCQs. There's a difference between the address of the instruction and then the instruction itself. Okay, so let me explain that. The question could ask you that what stores the current address. That is will be a different thing altogether from stores the current instruction. Okay, so let me indicate what the difference is. Assuming that location 0, the data contained here is binary. Okay, so assuming that technically we use the example 2x plus y. This is a data that is being stored in location 0. Okay, this could be allocated an address of, let's say, let's call the address 001. Okay, so let's say this is the address. An address is just like your house address. Your house address is not the people who live in the house or what the house contains. The house address practically indicates that this is Mr. Mensah's house. Okay, so when I give someone's my house address, and my house address is, let's say, BU 584. Let's say Mr. Ahin Street. Okay, that practically indicates that when you come to that particular house, you will find me there. Okay, but that address is not what is in my house, or as in the people who live in the house are different from their address. So let's take note of that here. So I'm just trying to indicate here that the instruction register does not store the address, but rather it stores the instruction. So in this scenario, what the instruction register will store here is the current instruction being processed, which is 2x. Okay, please, I don't know if we can see that. Let me write that in, no, behind. That'll be better. So let's say 2x plus y. That's the current instruction that is being processed. So the instruction register would literally hold that there. Okay, please, there is a similarity between the memory buffer register and the instruction register. And when we reach there, I'm going to explain that to you and note why I'm being specific about knowing the difference between the instruction and the address of the instruction. So let's say the instruction here is 2x plus y, and the instruction register is what stores it, right? And we are saying that basically the program counter is storing the address of the next instruction to be performed. So let's say here the address of the next instruction is 00011. That's too long. Let's just designate it as 00. Uh, let's just designate it as 010. Okay. Why is this thing just scrolling up and down? So let's just designate it as 010. Okay. So the program counter will basically hold the address of the next instruction, which is 010. Okay. And that tells you that when the computer is done processing this particular instruction, it is going to go to the next address, which is 010, and then perform or process that particular instruction. So we've now looked at the program counter, we've looked at the instruction register, we've looked at special purpose registers, the difference between them and then general purpose registers also. Now let us come and look at the next thing, which is memory address register. So it holds the address. Let's look at this. It holds the address of the data or instruction currently being accessed in the main memory. Okay, so it holds the address of the data that is being accessed currently in your instruction register. That is your MBR, which is memory buffer register. So we are basically saying that you see this 001 here will be stored in your memory buffer register. So 001. Because the job of the memory buffer register is that it only stores the address of the current program or current instruction that is being executed. And then your instruction register will store the actual instruction. So the memory buffer stores the address, your instruction register stores the instruction. Okay. So your program and then your program counter stores the address of the next instruction. So let us look at the next in line. So we have um, the the memory address register. We've talked about that. So the memory buffer register. Memory buffer register holds data to be transferred to or from the memory. Okay, so basically sorry, I've done a mistake here. Sorry. I was initially referring to memory address register, not memory buffer register. So please forgive me. So I was referring to memory address register instead as the address that stores the current location or the current address of the program or instruction that is being executed. And the memory buffer register, what it does is that it holds data to be transferred to or from the memory. Okay, so this holds data that is to be transferred to or from the memory. Okay, so this one, if you look at the arrows very well, realize that this communicates directly with the RAM. Okay, and what it does is that it picks data that is to be transformed here, and then after the CPU is done processing the data, it receives them and also sends them back into the RAM for storage. Please a second there. Okay, so let's continue. Okay, let's continue. So please, this is basically a coordinated process. So let's understand it as a process, okay? And not try to really chew the definitions or what they do individually, else it becomes very, very difficult to understand. So the reason why all these processes happen is because you are saying that your register here, okay, your entire register here serves as an intermediary between the CPU and the RAM. What it does is that it provides a computer a way to store interim data, okay, or data that would be needed, as in that is like needed or that would be used per time. Okay, it picks those data from the RAM. And what happens is that the memory buffer register picks the data that is the next data that is to be performed and then sends it here. And after the computer is done performing, the CPU is done performing that particular is done executing that instruction, it brings it back to the memory buffer register, and the memory buffer register sends it back to the RAM to be stored. Okay, and the reason why the RAM cannot interact directly with the CPU is because we are saying that the RAM is relatively slow. If we should allow the RAM to interact directly with the CPU, what will happen is that it will slow up the entire process of the computer. So we need to create an intermediate high-speed storage medium that can fetch data from the RAM and then code it so that immediately the CPU needs it, it will supply it to the CPU very fast. Okay, so we have something like a courier service. Instead of you to be at your home and then let's say drive all the way to wherever there is someone who has an Okada or who drives a motor, who has a motor, okay, and he's just saying that, look, I'll be your intermediary. I am fast. I am super fast. That is my job. You pay me, I'll come and take your food, and then I'll go and deliver it to the next person. Or you pay me, I'll go to the person, receive the items on your behalf, and come and deliver it so that I can do whatever I want to do with it. That is the registers. The registers are just helping speed up the entire computer processes by making sure that it creates an intermediate storage medium that is relatively fast and high speed and can receive data from the RAM in advance. And then when the CPU needs them, it supplies them. And to make sure this happens, it has created, or there are subunits that has been created. And one of them is a program counter. And what the program counter is doing here is that it will keep the location of the next program to be performed or executed. So once it has a location, now it means that the registers or the memory buffer register now has an idea of the next program that is to be performed. So what will it do? It now fetches the address of that program from the memory address register. Okay, so the memory address register will then fetch the address of that particular instruction, and then the memory buffer register picks that address and then forwards it up, and then it goes straight to your instruction register, which then stores the instruction which is to be performed. And then after it has stored that particular instruction there, that means it is ready for use by the CPU. Whenever the CPU needs it, it can now do what? Supply those instructions. Okay, so let us look at the next unit. Okay, we are saying that all these falls under what are special purpose registers, because look, we are saying that all these registers that we have mentioned here, they do not store general data. They have specific data that they store. The program counter stores the next data to be executed. The instruction stores the current instruction that is to be executed. And we are saying that the memory buffer register it stores, it receives data that is to be executed and also passes data that has been executed back to the RAM for storage. And the memory address register, what it does is that it stores the address of the current program that is being executed. Okay, so accumulator or the AC Please, it's not air conditioner, that's accumulator. So it holds intermediate results of calculations, okay? So your AC basically does what? It holds intermediate results of calculations that are being performed by the CPU, okay? So we can basically see that after all this, we have our general purpose registers, right? And the job that the general purpose registers does is that they store generic data. For example, there are some data that you feed to the system that the computer does not need it immediately. For example, if I feed a data like, let me illustrate, use an example to illustrate this. Let's say if I feed a data like, if I feed a computer an instruction, and the current instruction that I've fed to the computer is, let me know you use 2. I've abused 2, so let me use 3. So 3y plus z. Okay. And then after feeding this particular instruction to the computer to perform, I assign it a list of inputs or a list or a set of data. So I assign 5 as y. Okay. And I assign, let's say, 3 as z. And then I come to also specify another data, which is, let's say, a. And let's say a is 7. Let's say this A that is 7 is not relevant to this particular instruction that is being performed. But then I've issued another instruction which has been saved or stored in another location, okay, in our RAM. And that particular instruction is telling the computer to perform the operation, let's say 3y plus A. So currently, the program or the instruction that is being executed by the computer is 3y plus z. That means that automatically or currently 3y plus a is not the program being executed, which means that any data for a is not currently needed in the current operation. So that becomes a general data here, okay? It is not, if it was being used currently, we could have said that that data will have been stored in another place altogether. But now, since that data now becomes, I don't want to use the term a liability, or currently it's not being used, it has to be stored somewhere else. And that is where the general purpose registers comes in. So whichever data that does not fit into one of the data for the specific purpose registers, that does not fit into the program counter, the instruction register, the program status word, or the MBR, which is a memory buffer register, or the MAR, which is a memory address register, those programs will be stored in the general purpose register. Please, I hope we are all together. All right, so let's continue. Okay, so let's continue. I think, okay, I think, have I explained everything here? Okay, I think program status word has not been explained. Okay, so when we are talking about program status word, basically it indicates the status of the processor, okay, after executing an instruction. So after the CPU has executed an instruction, as the name suggests, the status of the instruction or the program that has been executed is assigned to the program status word. And then the program status word uses flags to indicate the status of the program that has been performed. So it uses, there are several of them. I think we have Z, C, O, and others, which I cannot recall. And these flags are used to indicate the result. of the last operation that was performed by the CPU. Okay, so let us move forward if everything here has been exhausted. So let us look at the size of registers. So the number and size of the registers in the CPU depends on the processor design. So it depends on how the processor was designed and can have an important impact on the performance and the capabilities of the CPU. Okay, so the size of the register is also very, very, very important. And it can depend the overall performance of the CPU. That is how fast or slow the CPU will run is dependent on the size of it's also dependent on the size of the registers. Okay, so we have several types of registers. When it comes to sizes, let's take note of that. With regards to sizes, registers can come in 8 bits, it can come in 16 bits, it can come in 32 bits, and it can come in 64 bits. So basically, if you want to remember this, just use the multiples of 8. Okay, so it basically comes in the multiplications of 8 or the multiples of 8. So we have 8, 16, we have 32, and 64. So basically 8 times 2, 16, 16 times 2, we have 32, 32 times 2, we have 64 bit register. So let us look at them one after the other. So the 8-bit register. So this holds 16 bits or 2 bytes of data. We know that 8 bytes makes 1 bit. Okay, so when we talk about 8 bits makes 1 byte, right? Yeah. So basically 16 bits is 2 bytes. Okay, so it holds 16 bits or 2 bytes of data. And they are found in older processors or certain systems that need oh goodness, I skipped the 8-bit. So let's talk about the 8-bit first. So this can store 8 bits or 1 byte of data. Please always know the conversion between bits and bytes. I think that's fundamental. So 8 bits is one byte, okay, and they are used for simple arithmetic and data manipulation, not for complex calculations or computation. So if your computer CPU register, okay, is based on the 8-bit system, or the registers are 8-bit registers, you should expect your computer to run by like snails, okay, because the main purpose of those is to perform basic arithmetic and data manipulation, not anything sophisticated or complicated. We are not even talking about sophistication and complication, not complicated, not anything normal, okay? So it is way below the normal. Okay, so the next is 16-bit registers. And 16-bit registers, they hold 16 bits or 2 bytes of data. And we said that 8 bits makes 1 byte. So 16 bits is automatically 2 bytes. So please, the reason I'm saying let's take note of this is that if something like this should be asked in objectives, probably, it could be presented in any or both formats. Okay, I don't know how a question could be framed under that, but it could be represented in both formats, and we should be ready for it. From our collective experience, which I believe is not only mine, but yours also, from last semester examinations, you get to understand that basically with MCQs, especially with this type of courses, the questions are not that straightforward. They would basically be very, very technical in nature, and that is something that we should anticipate, especially with regards to 102. Don't just study or read, but take note of the details, the technicalities, and be prepared for whatever happens. We cannot be able to predict with certainty, since past questions for that corresponds with our current mode of examination, which is online on site, it's not present for DCIT 102. All attempts to get hold of such past questions has proved futile. That means that we are practically in suspense. We cannot predict so much about how the objectives will be formulated or created. However, I believe probably the quiz gives us an indication of how it will look like. But let's just be prepared for all scenarios. So they are used for simple arithmetic and data manipulation. And the 16 bits, this holds 16 bits or 2 bytes of data, and they are found in older processors or certain systems that need 16-bit operations. And then we have 32 bits that hosts 32 bits or 4 bytes of data, and they are found in many modern processors and can handle large data size and more complex calculations, but not so complex, because currently in our current age, 32 bits is now becoming, I'm using the word becoming outdated. Okay, why? Because we are now having programs that are much more sophisticated in nature, and running them on this kind of devices would not be the best. So 64-bit registers, this holds 64 bits or 8 bytes of data, and they are used by modern processors, providing more computational power and better memory addressing capability. So we are saying that the most modern of all these 4 registers is the 64-bit registers. Why? Because it basically has more processing. It basically is able to hold more data and is used by modern processors. And this is very, very important because look, current programs that are being run, okay, on our computers and stuff are very, very like they are very, very intensive. Okay, there are some computers, if you run some kind of programs on it, it will just slow up and not. I believe we might have all encountered that before, even mobile phones and those kind of things. Look, you run some programs on it and then the computer starts dancing, especially if you are into things like video editing and those kind of stuff. You can be working and then in the middle of it, or your device breaks up, or you have to rest. Also, like Ubia, immediately you just open it up, you open the files, the computer says that I won't continue anymore. It just hangs up and it is not able to continue. That is basically because the the device that you are using does not have that capacity to process that amount of data that you are trying to feed it, or that you are trying to make it process. Okay, so if you are how do I call it? If you are into things like gaming, hard tasks like video editing, or you are into things like even graphic designing, a programmer, or into any profession that requires very, very intensive sessions with a computer, the most required is a computer that has 64-bit support, okay, in terms of its registers. So I hope we are all cool with that. All right, so we said most modern computers use 32-bit or 64-bit registers, resulting in the name 32-bit or 64-bit processors. Okay, and even now, most softwares and applications, they come in with specifications. There are some which have only 64-bit support. Please, we all know this, right? If you are installing applications, there's even some programs that we have the 64-bit versions, 32-bit versions. If you try to run 64-bit version of a program on a 32-bit computer, you shouldn't expect a very good result. If even the program is able to install at the first place, you should know that, look, you are putting your computer in serious danger. Gradually, it will start slowing up, and then you start experiencing a very, very, very funny behavior from it. Okay, so yeah. First to the width of the processor's register and how much data it can handle at once. So let us at the cache memory or the CPU cache memory. So the CPU cache memory is one of the most used types of cache memory and found on modern day CPUs. It holds data and program instructions that are likely to be needed by the CPU soon. Okay, so it enables storage and processing. It enables storing and providing access to frequently used programs and data. And the cache is slower than registers, but provides more storage space and faster than the main memory. And the CPU cache is embedded directly on the processor, while some are also installed close to the CPU. Okay, so we will have to talk more about cache because cache memory is a whole field on its own. But with the time now, I believe that we are limited. Okay, so I would want us to pause at the registers, and then we are going to take some questions or try to answer some questions from the previous section, which is section 1, because we are not only studying or we are not only learning, but we are doing this to also round up our preparations for our examinations. So we'll take some questions and then reward how do you call it? We will look to answer those, and then we can end today's section. So what I'm going to do is that I'm going to put another batch of questions on this current section on the platform, okay, tomorrow, so that we can all look at it, so that the next time we meet for DCIT 102, what we are going to do is that we are going to first answer those questions even before we begin this particular section. So okay, so let's get ourselves ready for that. So I'll stop sharing and let me share another. A minute. Section 1. Okay, so I'll be sharing my screen again. Let's have this here. Okay. So please, if you can see my screen, kindly indicate with a thumbs up or something so that I can be sure that we can all see the screen. All right, thank you. So please, this is going to be an interactive section because we are all going to try and then answer these questions together. This is based on section 1 and they are basic because section 1 was just an introduction to that, which contains some of the basic principles. Okay. So if we are all ready, then we can look to begin. Okay, so where there is confusion with the answers, we might refer to the slides for clarifications on that. So let's start with question 1. I believe we can all read, so we basically, I'll just read it once and then we'll look at the answers. So a computer is an electronic device that accepts input, processes it, and then produces what And A is a program, B is an output, C is an instruction, and D is a command. Okay, so who is answering this for us? We have to make this very, very fast. Okay, Mr. Interiba. Please, your mic is allowed.
The correct answer is B, an output.
Okay, so the correct answer is B, an output. So I would indicate the answers, and when I'm done, I'll send a file to the platform. That is the file with the answers that we had highlighted. Okay, so that is that for question 1. So question 2. What is the purpose of the input units in a computer system? What is the purpose of the input unit in a computer system? A, to provide data for processing. B, to display results. C, to store data permanently. And D, to perform arithmetic operations. So, Mr. Paul, Mr. Paul, please, you can.
Yeah, please, good evening.
Good evening, sir.
Please, the answer is A, to provide data for processing.
Okay, so the answer is A, which is to provide data for processing. And let's look at question 3. Which of the following is not a type of data that a computer can capture, store, or retrieve? Let's take note of this question very well. Which of the following is not a type of data that a computer can capture, store, or retrieve? A is numeric data, B is textual data, C is analog data, and D is audio data.
Analog data.
Okay, so analog data is the correct answer here. So
God damn it.
analog data. And then the next question, the ability.
Isaac,
Yeah,
is it analog or audio?
analog, goodness.
Analog.
How do I get this off?
I want us to get into something natural.
This thing doesn't want to. Okay, please let's move forward. We'll come back later and sort out this issue. I think we have very limited time, so we have analog data as a correct answer. This thing is supposed to. Okay, so let's continue. Let's continue. So question 4, the ability of a computer to be programmed to function automatically distinguishes it from other calculation devices. This characteristics is known as, we discussed this in the last section. So this characteristics is known as the ability of a computer to be programmed to function automatically. What is that characteristics called? We looked at the characteristics of of computers, right? We looked at things like it should be versatile, it should be programmable, and the rest. So, oh, I've even mentioned the answer. So please, someone should help us with the answer. Or Kayum, will you help us? Okay. Yes, sir. Okay, your microphone is, let me see. Okay, so please you can answer.
Yeah, I want to try. That's the accuracy. Is it the accuracy?
Not really. The accuracy is a characteristic of a computer that's, I mean, it's returning accurate output that corresponds with the input provided. So we said that the last time that when you give a set of data to a computer, it should be able, a set of instructions, I mean, it should be able to process it and return an accurate output. So that was accuracy. Here we are talking about the ability of a computer to be programmed. Let us even look at that. To function automatically. What is that characteristics called? Okay, so this is programmable, okay. So programmable basically refers to the ability of computers to be programmed to function automatically. Okay, so let's look at 5. What is the main limitation of a computer system? So the main limitation of a computer system, it can get tired of work. It can differentiate between right and wrong. It cannot learn from experience, and it can think on its own. What is the main limitation? So what is the main limitation here of a computer system? Who would want to answer this for us?
Alec,
Yes,
I will choose D.
you choose D. Okay, let's
It
see.
can think on its own. I think computers cannot think on its own unless someone input data for it to be able to process.
Yeah, computers cannot think on its own. But we're
Yes.
talking about the main limitation. So if you say it can think on its own is the main limitation, you just analyze that very, very well. A limitation should be something it cannot do.
Okay.
So when we say your limitations, it means something that is outside you.
Okay,
your
I
abilities.
understand. This one means it can think on it. Okay. So I was talking about computer cannot think on its own.
So, Mr. John, please, what then do you think would be the answer now?
Yeah, I think it will be C.
C. It cannot learn from experience. And we looked at this the last time. We are saying that if you're a graphic designer and you are designing a graphic for someone and you make a mistake, and the name of the school is, let's say, Jesus Cares Royal Academy. And let's say instead of Cares, Cares, you go and write Cares, which is Curse, which is like the other Cares, like Cares to Cares. And you go and write that Cares. Look, the computer, you are running 100 copies of that flyer or banner. The computer does not care. It will repeat that error throughout. It doesn't know whether there's an error or not. It only processes input and returns an output. Whether the output is wrong or not, the computer does not. And whether the input is wrong or not, it does not care. With a computer, it will process what you give it to it. No, If it has to repeat that thing 100 times, it will repeat that same error 100 times. And it doesn't care what happens, whether you lose your job or not. That's not the computers to think about. But let us speed up. So the speed of a computer is typically measured in watts. We stated this also the last time. The speed of a computer is measured in watts units. The speed of a computer is measured in watts units. Who would want to answer that for us? Mr. Jed.
Okay, it's measured in hertz. That's B.
It's measured in hertz. Okay. So hertz is a correct answer here. Okay, so the large storage capability of a computer is measured in watts units. The large storage capability of a computer is measured in watts units. In fact, this is very, very direct because everything there is not a unit for measuring storage for computers except one. So please, let's answer this quickly. Okay, Mr. Jed.
C. Byte.
Okay, byte. So yeah, byte. So byte is this. Is a unit for measuring computer storage. So question 8, which of the following components are the two fundamental parts of a computer system? So which of these two are all these are parts, and all these are important parts, but we're talking about fundamental parts of a computer. So input, output, CPU and memory, hardware and software, ALU and CU. So please, if you are asked to choose the two fundamental parts, which would you settle down for? Kayuni.
I think I'll go for the C, the hardware and the software.
The hardware and software are fundamental because every other operation depends on these two. You can classify every other component, every other operation falling under one of these two. So I believe these are the two main fundamental parts, so fundamental units. We are on 9. So the physical components of a computer system are referred to as. So I think this one, someone can just say it straight away. So the physical component of a computer system
is the hardware.
Is the hardware. What is software in a computer system? So the physical components, a set of instructions called a program, the process of storing data and the output produced by the computer. So for question 10, what are we settling on? So software. B. Okay, so a software is a set of instructions. So that determines the operations of the hardware. So the historical development of computers is described as, this is where everything gets a little technical. The historical development of a computer is described as a single invention by one person. We clarified this in the last section. B, a series of isolated discoveries. That's B. C, an evolutionary process due to continuous advancements. And D, the result of a single company's efforts.
Can we mention the answer?
Yes.
I think it's
with
C.
your time, it's C, sure. That's an evolutionary process due to continuous advancements. We said we cannot attribute the historical development of a computer to one person. Okay. Nobody invented a computer. It was the invention of different people, okay, and this wasn't invented as one unit, okay, but we had different inventions which were like a build up to what someone else had created. So someone created a punch card and made it an input device, and someone took the punch card and then updated the punch card into a keyboard, okay, because if you study how the punch card used to work, you understand a keyboard very well, and it's similarities to it. The punch card was just a card. You punch whichever instructions you wanted to input into your computer, you punch it on the card, okay. So you see physical punches on it, and then punch is not like blow, so like punch, 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 and then they insert it into the computer, and the computer is able to read. And if the computer wants to output, it also punches it on the card and then outputs. And then now on the mouse, we do the same thing. We've been punching letters, alphabets, and things. Okay, and then the mouse as well. So it's just a similar thing. So you could see that everything was just derived from someone else's invention, and the next person just built on it and made it better. So let's go to question 12. In the earliest use of the word computer in 1613, what did it refer to? So the earliest use of a computer, we said it referred to something. What did a computer refer to? So Mr. Nteriba.
I think a person who carry out calculation.
A person who carries out calculations was a computer. Was who a computer was called. Okay, so as at that time, now the whole concept of machines or devices being functioning or performing computing processes was not yet in existence. So it was a human being who carried out those calculations. And 13, which of the following is considered the first mechanical calculating device? A, Napier's bone. B, the Pascaline. C, the abacus. And D, the slide rule. Which
Is
of
C.
these is considered the first mechanical calculating device? It's C. That's Napier's invention. That's the Napier's bones. Was a mechanical calculating device that could perform which operations? So he said that John Napier's invention, which was a Napier bones, could perform which operations? So if we recall this, the Napier bones basically perform addition, subtraction, and division. That is the basic arithmetic operations. That was what the Napier bones was made to perform. And 15, who is credited with the invention of the slide rule?
Who is?
Not have much trust in it's they're setting a lot of questions on it. Like direct history, it becomes much of history than computing, though those history has relevance in computing, but it doesn't look so likely to me. But for the benefit of the doubt, sometimes you have to. It's better you prepare for that scenario and it doesn't happen than for you. So 15. Who is credited?
It's tough one, but I'll choose Pascal. Is it correct?
You choose A. Are you talking about A?
Yes.
Which is Blaise Pascal? No. The slide rule was William Alfred.
William Alfred. Okay.
Yeah. So the Pascaline, invented by Blaise Pascal, or the Pascaline machine, invented by Blaise Pascal, was a mechanical calculator that performed which operations?
Addition
So the function of the addition and subtraction. So we're saying that the Pascaline machine believes that all basic operations are born out of addition and subtraction. So if you have a machine that could perform addition and subtraction, You could use principles of addition and subtractions to perform multiplication and division, because basically we are saying that multiplication is just repeated addition, and and what have you. So 17 there, let's keep this, I don't know, but we can look at it on our own. Let's look at more important steps.
Hey, these are your questions. If
Okay.
the lecturer want to set these such questions, the problem will come.
Oh,
This
but
computer history things. It's
yeah,
too
it
boring. When you
depends.
are learning it, it's very, very boring.
Is it very true, very true, very true. It
It's
is very
boring when you are learning.
But, it's always dependent on the lecturer, what his main aim or what he aims to achieve in the examination. Some are not, they don't, some will not really care much about it, because when it comes to history, even with regards to 101, I didn't have a lot of this kind of things, because it's much more history oriented, and I believe, though it's important, but there are a lot more things that are important in terms of 102, DCIT 102, as compared to this. I don't know if you're getting me. So in order of importance, section 2 for me becomes one of my topics, as in section 2, 3, 4, like that sequence. Those are the sections where I'm expecting a lot more questions to come from, because looking at this particular man, that is like someone who would be giving questions from section 1. That's it. Those cheap things for you to just get correct. Look at his assignment that he's been given, and then some past questions of his that I've been able to see so far. Okay, which were all sitting, actually, not online on site. The kind of questions were not as friendly. Okay, so he doesn't look like someone who just wants people to pass freely like that.
I'm telling
He
you,
would
and he
really want
doesn't
to
even smile
scrutinize.
and talk sense.
Oh, but do you like one facilitator who mentioned the name? He's the most friendliest facilitator we have, but he's the one who really mafia us. I don't know if you know who I'm talking about. I'll not mention the name, because yeah. So I believe the session is being recorded. I don't want to learn strong. But regardless. Okay, so thank you. So let's end tonight's session. So I'll put a question on the platform.
Yeah. That would be the best. Myself, I want to do something.
And then we can all try our best to solve it. So I'm going to put another one, which is on section 2, so that we also try to solve that too. We'll discuss that when we meet the next time. All right. So have a very wonderful day, everyone. Let's meet at our next session. Reminds me tomorrow, actually, but let's see. Okay.